Hi, and welcome to the Unit 1A Solutions Chemistry video Part 2. Before we begin, I just want to quickly go back to CFU4, the answer, and how do we get those numbers. I think I rushed through that, so I just want to be clear on that. What we're trying to figure out here is which one of these has the highest NH4 plus ion concentration. We dissolve it in water, and when you dissolve salts in water, they sort of break apart into their ions, and the number of ions that you get will depend on how much you have in the formula of the compound. So for the first one, we only have one NH4, so its concentration would be the same because you just take the number that you have and then multiply it by the concentration of the salt. Here we have, for the ammonium phosphate, we have 3 NH4, so we take 3, that's subscript, and multiply it by 0.2, and that would give us a concentration of 0.6. And for the last, for the ammonium sulfide, we have 2 ammonias and the ionic compound, and so we take 2 and multiply it by its concentration 0.4, and that gives us 0.8. And so based on that the C had the highest concentration. All right, so with that being said, let's dive right into part 2. In the last part, we looked at what happens when you dissolve salts in water. Now we're going to look at what happens when you dissolve acids and bases in water. To sort of understand that, we need to know what an acid and bases are, and we also need to be able to identify them. For acids, there are 2 different things that we look for. You either look for a hydrogen in the front, that's the way we write their chemical formula, or you look for what's called a carboxylic acid or Cu group. That's where you have carbon, 2 oxygens, which could either be written out like this or as O2, and then a hydrogen. So those are acids. Bases, on the other hand, there are 2 types of those. You have metal hydroxide, so you have a metal and then you have an OH, and then there are also amines. Now amines, you'll see a nitrogen in the front, and then there are 3 things after, like 3 groups. So those groups can be hydrogens or hydrocarbons. When I say hydrocarbons, I mean things like carbon and hydrogen. So this would be ammonia, and then this one is known as methylamine. So this is a methyl group, and it's an amine. Okay, so based on what we just went over, your job is to identify these things as acid, base, neither, or both. The both is a little bit tricky, but why don't you do your best using the definitions that you know, and then when we come back together, the answers will be revealed. All right, let's start with the metal hydroxide bases. So these 2 are metal hydroxide bases. You see a metal, and then you see an OH afterward. The other base we know are amines, so that would include these 2 where you have a nitrogen, and then there's either it can be a hydrocarbon or it could be a hydrogen. All right, here we have our acids. Acids have hydrogens in the front, so these are the ones with the hydrogen in the front, nitric acid and phosphoric acid. We also have these 2 as acids. This is carboxylic acid, and this one also is a carboxylic acid because it has that Cu group or CO2H group at the end. Now let's look at some of the ones that are neither. First one is KNO3. So this is a salt, has a metal, and then that's non-metal part. Now technically these are also ionic compounds, but they're the way we'll be defining them are as bases. So they are ionic compounds, but the metal hydroxides are also bases. This one is neither because although it has an OH, there's no metal in front of it. So so this is not an ionic compound. This is just a molecular compound. In fact, this is ethanol. NO3 minus, you may recognize this as a polyatomic ion. You may also be thinking, well, it's a nitrogen with 3 things attached to it, so why isn't this an amine? And the main reason for that is that the 3 things, you have a choice. They can either be hydrogen or a hydrocarbon, which is a carbon with hydrogens in it as well. So this should maybe this type of moiety or a hydrogen. You can't have oxygens or any other thing like that. So this would be considered neither. And then finally, water is actually both. And I'm not going to explain it now, but you'll see that in a moment. Okay, so we talked before about dissolution, which means to dissolve, and we said things dissolve differently. So ionic compounds like salts and bases, and acids, which is a molecular covalent compound, breaks apart into ions. And the molecular base does not break apart into ions, but it forms ions, and polar molecules is a straight non-electrolyte. So in order sort of to understand how acids and bases dissolve, we have to define their give them definitions based on their chemical behavior. There are 3 definitions for acids and bases: Lewis acids and bases, and that's a very broad definition. And within that, you can have a Bronsted-Lowry or Arrhenius acid and base. And there's overlap between these, so something could be both a Bronsted-Lowry and Arrhenius as well. Okay, we're going to focus on, for simplicity's sake, we're going to focus on just Arrhenius for right now, and we're going to look at Arrhenius acid. So an Arrhenius acid is a substance that dissociates in water to form H+ or protons. So H+ are known as protons because that's the only subatomic particle that an H+ has. And I just want a quick note why we're just focusing on Arrhenius definition is because it kind of helps us to see what happens when we dissolve things in water, because that's part of the definition. Substance that dissociates, so dissolves in water, and tells you what happens when it dissolves. To see that with acids, it's a good idea to look at their structure. So there are different types of acids. We can sort of categorize them in different ways. Binary has 2 types of atoms. So like HCl, there's hydrogens and there's chlorines, or H2S. And so here, what I've highlighted are the acidic, they're known as acidic protons or acidic hydrogens in those acids. You also have oxyacids, which are usually polyatomic ions with hydrogens attached to them. And the number of hydrogens is equal to the amount of negative charge. So if you take something like a polyatomic ion like nitrate, NO3 minus, it has a -1 charge. That means we're going to have 1 acidic hydrogen attached to it when we form its corresponding polyacid or oxyacid. And that hydrogen is going to attach to the oxygen. All right, let's try it again for sulfate. How many hydrogens do you think this will have? All right, it should have 2, and they are going to again attach to the oxygens. All right, and then finally, another oxyacid will be like the Cu ones, and so once again, this also follows the same thing. -1 charge, it will have 1 acidic hydrogen. Okay, so now that we've seen what their structures look like, what happens when we dissolve them? If you take something like nitric acid, for example, when it dissolves, it's going to break apart into H+. So according to the definition, when you dissolve Arrhenius acids in water, they're going to form this H+, this proton. And whatever is left over, which would be the nitrate. Remember that according to the law of conservation of mass and matter, that you have to have the same number of atoms on both sides, so that seems to work out. And also the charges must be the same as well. So if you produce 1 proton, which has a +1 charge, then that'll tell you what the charge should be of the anion that you form. And this would have a -1 charge. So -1 +1 gives you overall 0 charge, which is what you expect because you have overall 0 on the other side. Okay, and this is what it would look like. You have HNO3, which I think is a liquid, and then it breaks apart into these two ions when aqueous ions when dissolved in water. Let's try that again with H2S. So once again, we're going to form hydrogens, or protons, I should say. How many protons are we going to form in this case? That's right, we're going to form 2 of those, and what we have left over is the sulfide ion, which has a 2- charge, because once again we want to make sure the overall charge is balanced out. And this is what this would look like when we write its chemical equation. All right, so it's your turn now. How many protons will each of the Arrhenius acids produce when dissolved in water? You're going to try this, and the first thing I would recommend you do is identify the protons or the acidic hydrogens in these compounds. Great, so these are the acidic hydrogens, and then now let's take a look at your answers. All right, so this is what your answers should look like. If you are confused about anything, please bring those questions to class. Okay, next CFU, you're going to write the dissolution, the reaction equation to show the dissolution of these acids. And what I mean by equation, it should look something like this. So that includes the phases as well. All right, when you press play again, the answer will be revealed. Okay, so here are the answers. This look like this. And if you have any questions or concerns, please once again, bring them into class. So note them here and bring them into class. Okay, we're now going to look at the bases. So Arrhenius definition says that a base will dissociate to form OH minuses. And that makes sense when we look at metal hydroxides because, hey, that's what they have in the OH minus. So when you dissolve in water, it breaks apart into the hydroxide. So let's look at an example of that. Looks very similar to what we did with the acids, except for now we're dealing with OH minuses instead of protons. So take calcium hydroxide, for example. Notice the subscript 2 outside the parentheses is telling me that we have 2 of the hydroxides. So we're going to form 2 hydroxides, and then of course the charge on calcium is 2+. And once again, we can figure out the charges based on our understanding that both sides must be neutral or our understanding of ionic compounds. And this is what this would look like. So we have our phases in and the number of ions that we form. All right, so in this CFU, you're going to identify how many hydroxides will each of the Arrhenius bases produce when dissolved in water. Pause the video now. When you press play, the answer will be revealed. Okay, and this should say OH minuses, so you want to change that here, and this should also say bases. Sorry, I didn't change that, but anyway, this should be bases, and this should be OH minus. But these are the correct answers, these number of hydroxides that are produced. Okay, now what about the amines, however? You may be thinking, well, what about those? Where does the OH come from there? So the thing with amines is that they are bases, but they do not fit the Arrhenius definition. So we're going to have to sort of use another definition, and that's going to be the Bronsted-Lowry, which means that for an acid, it's a proton donor, and for bases, they're proton acceptors. All the acids we looked at so far are considered Bronsted-Lowry. Acids, I won't really show that here, but just to note that they do fit that definition. But let's focus on the Bronsted-Lowry bases. Okay, so what do we mean by proton acceptors? In order to do that, to understand that, you have to see what happens when you put something like triethylamine in water. When you put it in water, the water itself, remember how I said water was both an acid and a base? The water itself is going to act sort of like an acid. What do I mean by that? The water is made up of 2 hydrogens and 1 oxygen. One of those hydrogen acts as an acidic proton, and then the other hydrogen gets together with that oxygen and forms like a hydroxide. So we can sort of split this together apart into H plus and OH minus. So the amine is going to accept the H plus from water. And so that goes with the nitrogen here. And then that leaves what's left over is OH minus. That's what we get there. So the OH minus that's produced in a solution from when you dissolve an amine in water is not from the amine itself, it's actually from the water. So basically the amine breaks apart the water, takes the hydrogen, the acidic proton, and becomes an ammonium. Notice the charge here is +1. And then what's left over from water is the hydroxide. So this is sort of the way that we write it out. The only difference here is that I wrote H2O as H2O, and the hydrogens usually go after the nitrogen. Let's look at another example with NH3 before you guys try it. So NH3 plus water, the amine is going to steal that hydrogen from the water and forming this ammonium, NH4 plus, and then what's left over from water is OH minus. And so we can write its chemical equation like that. Okay, so now it's your turn to sort of try that. You're going to write the equations to show the dissolution of barium hydroxide, and this is dimethylamine. Remember, for the amines, you also are going to want to show the water. Pause the video now, and when you press play again, the answer will be revealed. All right, so here are the answers. So I want you to note very carefully, make sure you check your work very carefully and to see that everything works out. There was a mistake here, sorry. This should have been a liquid. At the top, the dimethylamine should be a liquid, not a solid, and that's what I've written here. So sorry for that confusion. Please correct that and make that a liquid. All right, so we're going to pause the video now. I hope you have found this video helpful. I have at the end of your packet sort of the success criteria, things that you should be able to do after watching this video, and if you can do those things, that tells me that you've successfully completed this note packet. All right, I hope you found this video helpful. Have a quality day.